Hello and welcome to another lesson of working with vectors. In our previous lesson, we tackled the problem about crossing a river, and our boatman Ismail ended quite a long way away from his intended destination. Today, I will introduce you to a new idea, the idea of relativity. And by the end of this lesson, you will be able to label velocity vector diagrams and explain the concept of relative motion. No doubt, you may have heard that Albert Einstein developed a theory of relativity. Well, we are not going into his theory now. But let us simply use his idea that things may appear different depending on where you are watching an event from. Have you ever sat in a train and thought that it was yours that was moving, when in fact it is the train next to yours that is moving? Now let us try and illustrate this using two cars. From this viewpoint, what do you think is happening? You may think, based on this view, that this car is moving forward faster than the white car. But now, if we move our point of view, we get a different experience. So it is important as to where you stand when you observe something moving. We will use this idea when we label our vectors. Let's go back to our velocity vector diagrams now. I will quickly recap on the situation. Ismail is taking two children across a river. The river flows eastwards at 3 meters per second, while his boat moves at 4 meters per second. As Ismail attempts to get from A to B, the flow of the river takes him downstream to C, 300 meters from B. This is the diagram we worked with in our last lesson. There are three velocity vectors. They are the velocity of the water in the river and indicated here by the blue velocity vector. The black velocity vector shows the velocity of the boat as it heads due north. And finally, the yellow velocity vector is the resultant velocity of the boat. At the end of our previous lesson, we noted that the black and yellow vectors are both vectors that refer to the velocity of the boat, but clearly they are different. We need a better labeling system. We will use the idea of relative motion to do this. Let's go back to our blue vector. We know that the river flows downstream at 3 meters per second to the east. Now someone standing here will notice this motion. However, someone floating down the river watching the water would think that the water is not moving. The observer would notice no relative motion. So according to the observer floating downstream, the velocity of the water would be 0 meters per second. But to someone standing on the bank, the velocity of the water would be 3 meters per second downstream. So we label the blue vector as the velocity of the water at 3 meters per second relative to the river bank. Or relative to a stone which is in fixed position on the riverbed. Now if we were standing on the river's bank and watching the boat, we would see traveling in the direction of the resultant velocity. So the resultant velocity is the velocity of the boat which is relative to the river bank. Now let me go back and put this label in. So we label the resultant velocity as the velocity of the boat relative to the river bank. But what about the black velocity vector from A to B? We know that Ismail wanted to go directly north. He headed due north across the river at 4 meters per second and ignored the velocity of the water. Now if the water was not moving, Ismail would have been able to go straight from A to B. In fact, someone floating downstream would be able to observe Ismail heading directly north across the river. So the black velocity vector is the velocity of the boat relative to the water. It is not good enough to simply say that this is the velocity of the boat when we label the velocity vector diagram. As you can see that both the black and the yellow velocity vectors are velocity vectors that refer to the boat. so we must clearly distinguish between them. So we can say the yellow one is the resultant velocity, the velocity of the boat as seen from the river bank, and we have labeled it velocity of the boat relative to the river bank. And the black one is the velocity of the boat relative to the water. Are you beginning to see that we refer to velocity relative to some other reference point? Here you can see that there are 2 points of view or points of reference. The view of a person standing on the riverbank looking at the boat and the view of the person in the boat looking at the riverbank. Now let's return to Ismail and the 2 children crossing the river. Let me set the scene for you again. A river flows due east at 3 meters per second. Ismail wants to cross this river in his boat, which can move through the water at 4 meters per second. He is situated at point A on the river bank, and he intends crossing over to point B on the other side of the river. Point B is exactly due north of point A. Ismail wants to cross directly from point A to point B. In other words, he wants to go due north across the river. Now, if he was crossing a road, he would just walk straight across to get to point B. However, crossing a river, the flow of the river would carry him slightly downstream. Let's look at this graphically. If he headed north in his little motorboat with the intention of going from point A to point B, the current of the river will carry him and he will land up at point C, which is 300 meters further downstream. We worked this out in the previous lesson, but today we want to land Ismail exactly at point B. So the questions are, what is the velocity of the boat relative to the river bank? And what is the direction in which he should point the boat? It is always useful with these problems to stand back and take a bird's eye view of the situation. From this viewpoint, you can see that the velocity of the water in the river is 3 meters per second due east. We know that Ismail must land at B. So on the vector diagram, we can show 2 velocity vectors. The resultant velocity must be in the direction from A to B. The resultant velocity can also be called the velocity of the boat relative to the river bank. The other velocity vector is the velocity of the water, which is also relative to the river bank. Now, to fit all this together, we have the head of the green vector, which is the velocity of the water, meeting the head of the resultant velocity. This means that Ismail must move upstream in order to compensate for the flow of the river. This must be the velocity of the boat relative to the water. Now all we need to do is add in the given values of velocity to the diagram. The water in the river flows towards the east at 3 meters per second. And we have labeled this the velocity of the water relative to the river bank. Now Ismail points his boat in this direction. This doesn't mean that he has suddenly become stronger because he moves upstream. He can still only propel the boat at 4 meters per second. And we have labeled this velocity of the boat relative to the water. Now these 2 velocity vectors combine to give the resultant velocity of the boat, which we have labeled the velocity of the boat relative to the river bank. You can see that we have created a right angle triangle. So we can apply the theorem of Pythagoras to any calculations that we need to do. Let's find the magnitude of the resultant velocity, which is the velocity of the boat relative to the river bank. We know that the boat travels through the water at 4 meters per second, and the velocity of the water towards the east is 3 meters per second. We use the formula c squared is equal to b squared minus a squared. We know c is the resultant velocity. We will call it v, is equal to the square root of 4 meters per second minus 3 meters per second. Using your calculator, you will get an answer of 2.65 meters per second. So the resultant velocity of the boat, or the velocity of the boat relative to the river bank, is 2.65 meters per second. Let's find out in what direction Ismail must head in order to arrive safely at point B. The triangle of the velocity of vectors is a right angle triangle. So we will be using the sine ratio to find the value of theta. Sine theta is equal to opposite over hypotenuse. Now for our diagram, sine theta is equal to A over B. So sine theta is equal to 3 meters per second divided by 4 meters per second. And using our calculator, we find that theta is equal to 48,6 degrees. This means that Ismail will have to travel at a direction of 48,6 degrees west of north. Here is the task for today. It involves time. From the task in our previous lesson, you calculated that Ismail would have taken 100 seconds to cross the river if there was no current. We worked out that this was the same time as when he drifted downstream. Now the question we now ask is, how long does it take Ismail to cross the river when he heads upstream? Remember to use all the given information. We know that the river is 400 meters wide from A to B. The resultant velocity is in the same direction from A to B. We also know that time is equal to displacement divided by the average velocity. In our next lesson, we take to the skies and use our skills to solve a problem related to aircraft navigation. So until then, namaste and goodbye.